This video is about solving inequalities using the number line method. First, let's remember how to actually write the equations of polynomials. It's pretty easy to write the equation of a polynomial if you find the zeros of the polynomial. So in the case of number 1, the zeros are -5, -2, and +3. So you would write the equation as y equals a, which we have as some unknown multiplier in the beginning, times x plus 5 times x plus 2 times x minus 3. So those come from -5, -2, and +3 being zeros of the function. We write it in factored form. Then notice that there is a point at 0, -5. So we replace y with -5 and x with 0 in all of these spots, and then solve for a. So when you divide everything else over to the other side, you get a equals 1/6, and then you have the equation. Likewise, this would work for problem 2, where you have zeros at -3, 0, and 4. But one thing you notice about number 2 is that the zeros at x equals 0 and x equals 4 bounce off the axis instead of going through the axis. And so when there's a bounce, you would put a squared in the function. Then, since the y-intercept is at 0, we cannot substitute in the y-intercept. We're going to notice that there's a point at -1, 2, and then substitute -1 in for x everywhere. So notice that -1 minus 4 gives us -5, so it doesn't just show up as the number. And then I'll plug in 2 for y, solve for a, and get 1/25, and then I have this equation. Just as a reminder, if the function crosses the axis, it's not squared, so it's to the first power, it's regular. But if it bounces off the axis, like it did at 0 and 4 in the second problem, we write it as a squared. It's a 0 that has multiplicity 2. Now let's introduce the number line method. First, we're going to use the graph to determine the values of x where the function is greater than 0. So if I look at this graph and I look at the x-axis, the function is greater than 0 everywhere that the function is above the x-axis. So if I look at this, this will be where x is less than 0 or where x is greater than 4. Which we typically are going to write in interval notation, -∞ to 0, union 4 to infinity. Now let's find an equation for f of x. This is a parabola that has zeros at 0 and 4, so I'm going to write this in factored form, which I don't really need to put x minus 0, so I can just say x times x minus 4. And then I need to check what the a value is. Now, if I remember things about polynomials, I know that the typical parabola, typical quadratic, with an a value of 1 would go over to up 4. But let's say I don't remember that. I can just substitute -4 in for y and 2 in for x, and then solve for a and get a equals 1. So f of x is equal to x times x minus 4, since the a value is 1. Now what we're going to do is we're going to find the critical zeros or critical values from the equation in B. So what that means is we're going to take this function and we're going to set y equal to 0. We find out that x equals 0 or 4. And all the number line method is you figure out where the zeros of the function are, which we saw on the graph. We put them on the number line. And then we check every region of the number line in the function to see whether it's positive or negative. One thing that we know is that if the function, and this especially works because we're checking for whether the function is greater than 0 or less than 0 or something like that. If the function is greater than 0, one thing that we know is that the zero product property, which we've learned for quite a while, you just may not have had a name for it until last year in Algebra 2, the zero product property tells us that if the product of two or more numbers is equal to 0, at least one of those numbers must be equal to 0. So, in this case, either x is equal to 0 or x minus 4 equals 0, which gives us x equals 0 or 4. And something that helps us with all of these problems is that because the zero product property is true, if these are equal to 0 in the function, everywhere in between has to either be positive or negative, and it can't switch. So for example, if I plug in 6, notice that my function is positive. If I plug in 7, it would also be positive. 8 would also be positive. 5 would also be positive, because the function never hits 0 over here. The function can't cross the axis because there are only two places where the function crosses the axis, at x equals 0 and x equals 4. So because of that, once I figure out that any number over here is positive, all of the numbers over here are positive. And that's true for any other region. So if I plug in 2, for example, I figure out that this function would be 2 times negative 2. That's negative. Every number in this region is going to be negative. If I plug in any number to the left of 0, like negative 1, I get a negative times a negative, which gives me a positive in the function. Since the function has no other zeros, every other number over here must also be positive. Therefore, all I have to do is write a number line, plug in one number from each region, and that will tell me whether every part of that region is positive or negative. And that's very helpful because I can solve questions like, is f of x greater than 0, by just figuring out where the critical points are on f of x, the critical values, and then subbing in numbers from each region and figuring it out. So if I'm looking for greater than 0, I look for the areas that have a positive sign, looking for a plus. So I would write negative infinity to 0, union 4 to infinity, which is the same thing that I got in part A. Notice there is no such similar thing to the zero product property for any number other than y equals 0. So this won't work. For example, if I had x times x minus 4 equals 1, I can't say that x equals 0 and x equals 4 work. Like, I can't just take things and figure out where this equals 1, and that's not going to work. There's actually an infinite number of things when I multiply them together that they would equal 1. So that can't work. It only works for 0. Now, problem 2. Similarly, I would try to figure out where this is less than 0. So I look at the graph, and this function is less than 0 everywhere between x equals negative 2 and x equals 1. Now if I want to write an equation, I would use factored form again. So f of x equals a times x plus 2 times x minus 1. If I subbed in the point 0, negative 2, I'd find out that a equals 1 again. So f of x is equal to x plus 2 times x minus 1. Now I'm going to take this, figure out where my critical values are. Notice that if I set f of x equal to 0, I'm going to find critical values at negative 2 and 1. These are my only zeros in the whole function. So that means I can check each region. If I plug in, let's say, 4 or 5 or 100, I'm going to end up with a positive times a positive. If I plug in 0, which is somewhere between negative 2 and 1, again, I could plug in any number between negative 2 and 1, but 0 is an easy one to plug in. I'd get 2 times negative 1, which gives me a negative number. If I plug in negative 10 or negative 20 or anything like that, I'd get a negative times a negative, which gives me a positive. So my answer is everywhere this function is negative, between negative 2 and 1. So my answer is negative 2 to 1, which is the exact same thing we got in A from the picture. Notice that from negative 2 to 1, this function is negative. Let's do a couple practice problems. On what interval is the line greater than the polynomial? So we have the line y equals 12. All we have to do is look at the picture, and we figure out that the line is higher than the polynomial everywhere to the left of 3, with the exception of at 2. At 2, the function and the line and the polynomial are equal. So I would have negative infinity to 2 union 2 to 3. Problem 2, something that's tempting, we have to remember that the zero product property only works when the function is equal to 0. So it might be tempting for us to think that if we do x equals 4 and x equals negative 2, we might be able to put those as critical points on a number line. However, those numbers will not make anything equal to 7. Therefore, that's not going to help us very much. So what I'm going to do, if I want to solve this algebraically, is I'm actually going to distribute this. So if I distribute that all out, I get x squared minus 2x minus 8 is greater than 7. Subtract the 7 over and factor again. So I have x minus 5 times x plus 3 is greater than 0. That's something pretty easy to do with the number line method. So negative 3 and 5. If I substitute in anything smaller than negative 3, negative times a negative is a positive. If I substitute in anything between negative 3 and 5, like 0, I get negative times positive. And anything big, I get positive times positive. So I'm looking for where this is a positive number. So my answer would be negative infinity to negative 3, union 5 to infinity. If I look at the picture of this graph, what I see is that's exactly what happens. I have everything to the left of negative 3, everything to the right of 5 is where it is greater than 7. So notice if I get this equal to 0, I can solve this algebraically pretty easily. Number 3, this is already equal to 0, or less than or equal to 0. So I'm going to just get my 3 critical points, negative 3, 1, and 5. And then I start substituting numbers in. If I substitute in something pretty big, I have like 10 or 100, positive, positive, positive. So everything's positive. That would give me a positive number. If I substitute in something like 2, I get negative 3 squared, which is 9, times 1, times 5. That's also positive. If I substitute in something here, like 0, I get positive, negative, positive. If I substitute in something way to the left, I get positive, negative, negative. So multiply all those together, I get a positive number. And so where is this less than or equal to 0? From negative 3 to 1, And also, at 5, don't forget that at 5, this actually does equal 0. So my answer would be negative 3 to 1. These are actually brackets because the equal to does count. So those make it equal to 0. And curly bracket for 1.5. The last thing we should talk about here is we also, once we start figuring this stuff out, we don't really need to plug in points all the time if we understand how polynomials work. So remember, if a function has a squared, it's going to bounce. And so that means this went from positive to positive. This went from positive to positive. Whereas this one was not a squared. It crosses the line, negative to positive, or vice versa. Negative to positive, positive to negative, negative to positive. Therefore, if I look at this problem, it's pretty obvious that from 5, on both sides of 5, I'm going to have a positive number because it's going to bounce at 5 if I graphed it. But these two would have switches and signs because they do not have squareds. So that's something that is hopefully pretty logical. So my answer is negative 3 to 1 with brackets union 5. Lastly, remember that x cubed plus 8 would be factoring with SOAP. So x plus 2, parentheses x squared minus 2x plus 4. This part never, ever, ever factors further. So the only thing that actually works to make this equal to 0 is negative 2. And I figure out where this is greater than 0. If I substitute in a really big number, it's going to be positive, and to the left of 2 it would be negative. Also remember that x cubed plus 8 is just the cube graph parent function moved up 8. So if I graphed it over here, I would see that this is where the function is greater than 0, anywhere to the right of negative 2.